Imagine building a mirror in space. Not just any mirror, a mirror so enormous that it would be larger than the entire continent of Africa. Its mission? To shine extra sunlight onto Mars until the planet begins to warm. It sounds like something straight out of science fiction, but it isn't. This idea has been proposed by real scientists, published in peer-reviewed journals, and debated by researchers who've spent their careers studying the red planet. The surprising part, though, isn't that someone suggested it. It's that other scientists looked at the exact same evidence, ran the exact same physics, and reached the opposite conclusion. One side believes terraforming Mars has finally moved from impossible to merely unimaginably difficult. The other argues it's still so far beyond our industrial capabilities that it might remain impossible for centuries. So, who's right? And more importantly, what would it actually take to transform a frozen, lifeless world into a place where humans could survive? Today, we're going to follow the evidence, examine both sides of the debate, and discover why the real answer is far more complicated than a simple yes or no. Before we can answer that question, we need to understand what terraforming actually is. The word itself sounds like it belongs on the cover of a science fiction novel, and for most of the 20th century, that's exactly where it lived. But over the past few decades, something changed. Terraforming didn't leave science fiction. It entered science. At its core, the idea is remarkably simple. Take a planet that cannot support life and gradually reshape it until it can. Warm the surface, thicken the atmosphere, create a stable water cycle, shield the planet from harmful radiation, and eventually produce enough oxygen for people to breathe without a spacesuit. Among every world in our solar system, Mars has always been the obvious candidate. Not because it looks anything like Earth today, but because billions of years ago, it may have. Evidence suggests that rivers once carved across its surface. Lakes filled enormous impact craters. Some scientists even believe an ocean once covered much of the northern hemisphere. Then, something happened. Mars lost most of its atmosphere. Its surface water disappeared. The temperatures plummeted, and the planet slowly became the cold, dusty desert our rovers explore today. Which leads to an extraordinary question. If Mars was once a world that could support liquid water, could it become one again? That is where the scientific debate truly begins. For decades, the answer seemed obvious. Terraforming Mars, a fascinating idea, but nothing more than that. Scientists talked about it. Science fiction embraced it. But almost nobody treated it as a serious engineering challenge. It was a thought experiment, not a roadmap. Then, almost quietly, the conversation began to change. Over the last few years, a small group of researchers has argued that we may have been asking the wrong question all along. Maybe the biggest obstacle was never physics. Maybe it was technology. In 2025, Dr. Erica de Benedictis and 11 planetary scientists published a paper that challenged decades of conventional thinking. Their message wasn't that terraforming Mars had suddenly become easy. Far from it. Their point was something much more subtle. 30 years ago, terraforming wasn't just difficult, it was impossible. Today, it may simply be unimaginably difficult. That sounds like a small difference. In reality, it's the difference between fantasy and engineering. Think about building a bridge across an ocean. A century ago, that idea would have sounded absurd. Today, it would still be one of the largest engineering projects ever attempted, but nobody would argue that it violates the laws of physics. According to de Benedictis and her team, Mars is beginning to fall into that same category. The planet hasn't changed. It's still freezing cold. Its atmosphere is still incredibly thin. Its surface is still bombarded by radiation. What's changed is us. Reusable rockets have dramatically reduced the cost of reaching space. Climate models can now simulate entire planetary systems with remarkable accuracy. And synthetic biology has reached the point where scientists can design organisms for tasks that evolution never had a reason to solve. Taken together, these advances open doors that simply didn't exist a generation ago. And that led the researchers to ask a bold question. What if we stopped trying to transport massive amounts of greenhouse gases to Mars and instead built something far more efficient? Their proposal is surprisingly elegant. Rather than shipping billions of tons of material from Earth, they suggest manufacturing microscopic conductive particles using resources already found on Mars. Each particle would be only a few micrometers long, far too small to see with the naked eye. But together, they could act like an artificial greenhouse blanket. They would scatter more sunlight toward the surface while slowing the escape of heat back into space. According to their models, these engineered particles could warm Mars thousands of times more efficiently than carbon dioxide, gram for gram. It's a remarkably simple idea, and for the first time in decades, terraforming Mars no longer sounded like pure science fiction. It sounded like an engineering problem waiting for an answer. For a moment, it seemed as though humanity had finally found the first realistic path toward transforming another planet. Then, someone decided to check the numbers. The proposal was exciting. For the first time in decades, terraforming Mars seemed to have something it had always lacked: a realistic plan. The physics made sense. The models were promising. Everything seemed to point in the same direction. But every ambitious idea eventually faces the same question: what would it actually take to build? In 2026, astrophysicist Dr. Slava Turyshev from NASA's Jet Propulsion Laboratory decided to find out. He wasn't trying to prove anyone wrong, and he wasn't trying to prove anyone right. He simply did what scientists are supposed to do. He took the most promising terraforming proposals and started running the numbers. Not just the physics, the engineering, the manufacturing, the logistics, the industrial scale. Could humanity actually produce enough material? Could we transport it, deploy it, maintain it? That's when the conversation changed completely. Imagine someone unveils a blueprint for the tallest skyscraper ever conceived. The design looks flawless. The physics checks out. Then, an engineer asks a different question. How much concrete would it require? How much steel? How many workers? How many decades? Turyshev approached Mars the same way, and the answers were staggering. One proposal suggested warming the planet using gigantic mirrors placed in orbit around Mars. The concept itself works, at least on paper. The problem is the scale. According to Turyshev's calculations, it would require roughly 70 million square kilometers of reflective surface. That's more than the entire continent of Africa. Not a single mirror, but an enormous orbital structure assembled piece by piece, precisely aligned with the sun and maintained indefinitely. And that would only accomplish the first step. Making Mars warmer doesn't make it habitable. After warming the planet, you still have to give it an atmosphere people can actually breathe. According to the calculations, that would eventually require producing around 820 quadrillion kilograms of oxygen. Numbers that large are almost impossible to picture. So let's translate them into something more tangible. The most practical way to produce that oxygen would be to extract it from water. But doing the math leads to an astonishing result. You would need the equivalent of about 6 cubic meters of water for every single square meter of the Martian surface. Imagine trying to supply that amount across an entire planet. At that point, you're no longer talking about a construction project. You're talking about moving oceans. And that's what makes Turyshev's work so important. He never concluded that living on Mars is impossible. In fact, his conclusion is much more nuanced. Regional habitats, sealed domes, greenhouses, self-contained settlements, those appear to be well within the reach of technologies we're already developing. The real obstacle is something far more ambitious: transforming an entire planet. Open skies, a breathable atmosphere, a world where people could walk outside without a pressure suit. According to his analysis, the laws of physics don't stand in the way. Our industrial civilization does. So, who's right? The optimists or the skeptics? The answer turns out to be far more interesting than choosing sides, because in a way, they may both be right. After hearing those numbers, it's tempting to think someone has to be wrong. Either the optimists underestimated the challenge, or the skeptics proved the dream is impossible. But what if neither is wrong? What if they're simply answering different questions? The optimistic researchers never claimed that Mars could become a second Earth within our lifetime, or even within the next century. Their argument is much more restrained. The science may no longer be the biggest obstacle. Time is. Because terraforming a planet was never meant to be a project for one generation, or even 10. It's the kind of undertaking measured in centuries and finished, if ever, by civilizations that don't exist yet. When scientists imagine how such a transformation might unfold, they usually divide it into 3 major stages, each one dramatically longer than the last. The first stage is warming the planet. Not enough to create beaches and forests, just enough for liquid water to exist. At least in some places, for at least part of the year. If technologies like engineered nanoparticles perform as current models suggest, some optimistic estimates place this milestone within about a century. 100 years sounds like a very long time, but on a planetary timescale, it's almost the blink of an eye. Then comes the second stage, and unlike the first, it wouldn't be spectacular. There would be no lush landscapes, no towering trees, no animals roaming across the surface. Instead, scientists envision introducing specially engineered microorganisms capable of surviving the harsh Martian environment. Tiny pioneers, slowly spreading across the planet, patiently altering the chemistry of their surroundings. It may not sound impressive, but Earth began the same way. Long before forests, before dinosaurs, before humans, our own planet was transformed by microscopic life working quietly over billions of years. On Mars, history might begin with microbes once again. Then comes the final stage, the one that dwarfs everything before it. Building an atmosphere dense enough to protect the surface from radiation and rich enough for humans to breathe without life support systems. This is where Tereshev's calculations become almost overwhelming. Even if the technology works exactly as intended, even if humanity never abandons the project, and even if nothing major goes wrong, this phase would likely take thousands of years, possibly much longer. And there's another complication. Mars no longer has a global magnetic field. Without that natural shield, the atmosphere we spend centuries creating could slowly leak back into space, just as the planet's original atmosphere appears to have done billions of years ago. In other words, Mars wouldn't simply wait to be transformed. It would spend every moment trying to become Mars again. And that's why this debate isn't really about optimism versus pessimism. Both groups accept the same physics. Both agree on the same destination. What separates them is the question they're asking. The optimists ask, can humanity eventually do this? The skeptics ask, can humanity do this with anything resembling foreseeable technology? Those aren't the same question, which means they don't have to produce the same answer. But just when it feels like we've identified the greatest obstacle of all, another question quietly enters the conversation. And unlike engineering or physics, this one has no equation. It's a question about ethics. For the past several minutes, we've talked about engineering, orbital mirrors, nanoparticles, atmospheres, factories, thousands of years of industrial effort. But there's one question that has the power to change this entire conversation. And strangely, it's usually the last one people ask. Before we decide how to transform Mars, shouldn't we find out whether it's already alive? Not intelligent life, not cities, not alien civilizations, something far smaller, microbial life, simple organisms that may have survived beneath the surface, protected inside ancient ice, or hidden within pockets of salty underground water. At this moment, no one knows whether they exist, and that uncertainty changes everything. Imagine spending centuries developing the technology to remake an entire planet, only to discover that it already hosts its own form of life. Tiny, invisible, completely unlike anything on Earth, but alive nonetheless. Suddenly, terraforming stops being an engineering problem. It becomes an ethical one. Would we have the right to replace an alien ecosystem with one of our own, even if that ecosystem consisted of nothing more than microscopic organisms? Or would preserving the first extraterrestrial life ever discovered become humanity's highest priority? This isn't a philosophical question for the distant future. It's already influencing the decisions we make today. For years, one mission was expected to bring us closer to an answer: Mars sample return. Its goal was straightforward: retrieve the rock samples that NASA's Perseverance rover had already collected and bring them back to Earth for detailed analysis. Those samples could tell us whether Mars once supported life or perhaps still does. But in 2026, after years of rising costs, the mission was canceled. The samples remain exactly where Perseverance left them, waiting, alone, on Mars. There's something almost poetic about that. We're debating how to reshape an entire world before we've answered the most fundamental question about it. Is it truly empty? One of the co-authors of the optimistic terraforming paper, planetary scientist Edwin Kite, has argued that living planets are simply better than dead ones. It's a compelling idea. If Mars is truly sterile, then bringing life to an otherwise lifeless world could become one of humanity's greatest achievements. But that entire argument rests on one remarkably small word, if. Because today, we still don't know which version of Mars is real, the one that's completely dead, or the one that's simply waiting to be discovered. And until we answer that question, every conversation about terraforming begins with an uncertainty we cannot afford to ignore. Maybe the greatest challenge isn't building mirrors the size of continents or producing unimaginable amounts of oxygen. Maybe the greatest challenge is having the wisdom to understand a world before we decide to change it. So, can we actually terraform Mars? The most honest answer is yes and no. Nothing in the laws of physics says it can't be done. Terraforming Mars isn't like building a perpetual motion machine or traveling faster than light. Nature doesn't forbid it, but there's a world of difference between something being possible and something being practical. Today, we know how to imagine the technology. We know how to simulate it. We know how to calculate it. What we don't know is whether humanity will ever possess the industrial capacity to build it. And that may be the most important shift in this entire debate. For decades, scientists argued about whether terraforming belonged in science fiction. Today, they're arguing about engineering, energy, manufacturing, logistics, timelines. For the first time, Mars isn't just inspiring storytellers, it's forcing engineers to think on a planetary scale. That alone is extraordinary. But there's one idea I find even more fascinating. Throughout this video, we've talked about warming a frozen world, building an atmosphere, creating oceans, and spreading life across an entire planet. Yet the most important question may never have been, can we change Mars? It may be, do we truly understand Mars before we try? Because there's an enormous difference between bringing life to a lifeless world and replacing a world that already has life of its own. Right now, we simply don't know which version of Mars is waiting for us. And until we answer that question, patience may be our greatest scientific achievement. At the beginning of this video, I told you about an idea that sounds almost unbelievable. A mirror in space, larger than the entire continent of Africa. Ironically, that may not be the hardest part. Building a mirror requires engineering. Building an atmosphere requires time. But deciding the future of an entire planet requires wisdom. Mars has been waiting for more than 4 billion years. It will still be there tomorrow, next year, next century, long after every person watching this video is gone. Maybe that's the greatest lesson Mars has to offer. Not every frontier is meant to be conquered as quickly as possible. Some are meant to be understood first, because sometimes the greatest step in exploration isn't reaching farther. It's knowing when we're not ready. If you enjoyed this investigation, subscribe to Past the Edge, because next time we're going beyond another edge.